Hello, and this is Dr. Harris again, welcoming you to our first video for Chapter 6, where we're going to explore inferential statistics techniques for categorical data in more depth. In some sense, this video will be a review of some things that we did in the last video for Chapter 5, but it will also we'll introduce a new RStudio command, which does a lot of our work for us, but I'm still going to be asking us to be able to find confidence intervals and perform hypothesis tests in a couple of different ways. So just a reminder of where we are. We're talking about single proportions. So we're collecting categorical data from a sample, and we're measuring the percentage of the sample that meets a certain characteristic. And so since we have categorical data here, we can calculate the number of individuals who meet our condition, give our desired response, and we can let X be the number of such responses. If N is our sample size, then we can compute a sample proportion. We've used p hat as our symbol for sample proportion. And so we want to remember that p hat is the number of successes in our trial divided by the number of trials that we have. So let's work through a problem that got introduced at the end of the previous slideshow, the last slideshow for Chapter 5. Suppose that there's an proposed amendment to the state constitution coming up in a particular state, and a polling firm is interested in finding out if there's a majority position, pro or con, regarding this amendment. And so P is going to be our population proportion. It's the proportion of residents in the state who plan to vote for the amendment. And our sample is going to be 400 randomly selected residents of the state. They're asked, do you or do you not intend to support this amendment? It turns out that 186 out of those 400 say yes, they plan to support the amendment. Our sample proportion in this case then would be the number of successes, 186, divided by the number of trials, 400, or 46.5%, 0.465. So if we're going to form a confidence interval from this data, and we're going to perform a hypothesis test based on this data, we need to remind ourselves of a few things. First of all, we need the success-failure condition to be met, and then we need to be able to compute standard error. And the form that we use for standard error is going to be the same in both cases, but we're going to be using slightly different numbers in those calculations. So we have the success-failure condition that needs to be met, and we need to have observations be independent of each other. The independence is met pretty easily here. When we have a random sample, we can assume that responses are indeed independent of one another. And if we have 186 successes out of 400 trials, that means we have 214 failures. Both are easily much bigger than 10, so we meet the success-failure condition. So if we knew the population proportion, we could calculate the standard error as the square root of p times 1 minus p over n. But of course, in situations like this, we aren't going to know the population proportion, and so therefore we will approximate the standard error by replacing p with p hat. So our standard error for our confidence interval will be the square root of p hat times 1 minus p hat over n. If we want a 95% confidence interval, we're going to use z star equals 1.96, remember, but in general, we have different levels of confidence, and so we don't want to have a 1.96 in here automatically. That will depend on what the confidence level is, what multiplier goes in here. But in general, our form for a confidence interval in this situation with a single proportion, it's going to be the sample proportion minus the multiplier times the standard error to the sample proportion plus the multiplier times the standard error. So for a 95% confidence interval, 0.465 is our sample proportion, 1.96 is our multiplier. We use p hat, 0.465, in our formula for standard error. And so the lower limit of our confidence interval is going to be 0.416. The upper limit, when we add the margin of error, we're going to get 0.514. So we're 95% confident that the percentage of likely voters who plan to vote for the amendment is somewhere between roughly 41.5% and 51.5%. So what's the value of the margin of error in this case? Well, remember the margin of error is really the distance between the sample proportion and either of the endpoints of our confidence interval. Or you could think about it as the value of, in this case, 1.96 times the square root of 0.465 times 1 minus 0.465 over 400. And the difference between 0.465 and 0.514, for instance, is almost 5%. And so our margin of error in this case is around 5%. A little bit later on in the slideshow, we'll look at a formula that relates sample size to margin of error. So as we can see, to calculate a confidence interval, we just need to know the confidence level, and therefore Z star. We should have a calculator on hand. If we know p hat, then we can p hat and Z star, then we can, and I guess the sample size as well, we can easily calculate the endpoints of the confidence interval, interpret it using the formula that we have from a couple of slides ago. So if I want to perform a hypothesis test on this, in this scenario, recall we're trying to decide whether there's a majority opinion or not. So that means if there were no majority opinion, that means that the proportion would be exactly 1/2. Whereas the alternate hypothesis is going to be that that's wrong, that it's not 1/2. Recall that we're using a two-sided alternative hypothesis. And so remember in our hypothesis tests, we proceed as if the null hypothesis is true, which means we're going to assume that the population proportion value is 0.5. And so we need to find an interval to enter into p-norm GC. You recall that from the last slideshow in chapter 5. So we've determined how far away we are from the null value. That's 0.5. So 0.465 is 0.035 below the null value. So we need to find the number that's on the other side. So we're going to add 0.035 to our null value 0.5 to get 0.535. So the interval that we're going to enter in p-norm GC is C from 0.465 to 0.535. Our standard error is not the same as what it was for the confidence interval. Remember, we put the null value in for our proportion in calculating the standard error. And so in this case, it's going to be the square root of 0.5 times 1 minus 0.5 over 400, which turns out to be exactly 1/4. So 1/4 is our standard error in this case. So p-norm GC is going to be, we put these values in, and we get out that our p-value is 0.1615. What does that mean? It means that under the assumption that there is no majority view, that is, the null hypothesis is true, that is, that p is 0.5, the probability of getting a sample proportion that is 0.035 away from 0.5, 3.5 percentage points away from 50% or farther, is about 1/6. So it would happen about 16% of the time. Since 0.16 is greater than 0.05, that's the standard against which we compare the p-value, we're going to fail to reject the null hypothesis. Recall that if the p-value is bigger than 0.05, we fail to reject the null. If it's less than 0.05, we reject the null. So we don't have strong evidence in this case to reject the claim. So we might think that there's not a majority view, but our data doesn't support that. So even though only 46.5% of the sample said, yes, I plan to support it, that doesn't exclude the possibility that there really is a 50-50 split in the state. And I will point out that our confidence interval and hypothesis test results do match. 1/2 was in the confidence interval, and we failed to reject. And that matches what we talked about in the last slideshow for chapter 5. But now I want to introduce you to a command in RStudio that will perform both the confidence interval and the hypothesis test all at one time. And I've gotten in the habit over the last couple of years of calling these such commands one-stop shopping commands, because they do it all for us. Of course, we need to check the conditions before we apply the commands, but we're generally, but they're very powerful once we start using them. So we'll see various one-stop shopping commands in chapter 6 and 7. The first one for a single proportion is binom test GC. And so what we do, there are two different ways we can apply binom test GC. In this case, we had summary data. That is, we didn't have a file in our studio that had all the data in it. We actually just reported back how many trials there were, how many successes there were. And so what we need to do for binom GC is we tell it the number of successes using the variable x. So x is going to stand for the number of successes. So x equals 186. N is the number of trials. N equals 400. We're going to give the confidence level using the option conf.level. It's 0.95. In this case, if we want a 95% confidence interval. Our null value is going to be p. So p is 0.5. Alternative is 2-sided. So we're going to put that in there to run this. And then graph equals true will give us graphical output. So let's run binom test GC and see what we get. So I move over to RStudio. I input it. And I'll show you the output that we get here. And the graph equals true is the command that indeed gives us this graph over here in our plots window. But we can see a wide range of interesting output. I'm going to go over these in the next couple of slides, but we're told how many successes, how many trials there were. Here's our value of p hat. Here's our value of the standard error. And here's our confidence interval, and then our hypotheses, and then we get the p-value down here. So let's take a look in a couple of slides. So this is just, again, copying and pasting from that output. We're told how many successes, how many trials, p hat, the standard error. Here's our confidence interval, a little bit different from what we have, but pretty close, still about 41.5% to 51.5%. Our hypotheses, this is the two-sided symbol, not equal to. And then our p-value is a little bit bigger than the one we had before, but it's in the neighborhood of what we had. No, don't quite match up, but since our p-value is still bigger than 0.05, we're going to reject the null hypothesis. Okay, so we can do confidence intervals by hand. We can do hypothesis tests using pnorm-gc, and then we can use our one-stop shopping command binom test GC. That was looking at a case where we had summary data. We didn't have a data set to work with within our studio. Now let's look at an example where we have the existing data already input into our studio. The research question in this case is, do 50% of students at Georgetown College say they get enough sleep on average? We've got this data in the variable enough_sleep in the MAT111 survey data set. As usual, we're going to define our parameter ahead of time. P is the proportion of Georgetown College students who will say they get enough sleep at night on average. So we're expressing our parameter in words. We want to get good at that. If we want to check our conditions, we need to use our old friend xtabs. So I do xtabs and then tilde, variable name, enough_sleep, data equals dataset, MAT111 survey in this case. And we see we get 46 no's, 25 yeses. We're going to assume that a yes is a success here. So our sample proportion is going to be 25 divided by 71. I get 71 by adding the 46 no's to the 25 yeses. So our sample proportion is a little over 35%. And since we have more than 10 successes and 10 failures, we feel comfortable about proceeding. We're going to assume that these students that were surveyed form a representative sample of Georgetown College students. So is 35% too low, in some sense, to believe that half of Georgetown College students will indeed say they get enough sleep? Let's find out. You can form a confidence interval very quickly. Let's do a 90% confidence interval just for variety this time. Z star for a 90% confidence interval is 1.65. And so we're going to put our sample proportion, 0.3521, minus Z star times the standard error, p hat times 1 minus p hat over the sample size. and we're going to get just under 26%. And then if we add 1.65 times the standard error to 0.3521, we're going to get about 44.5%. So we're 90% confident that the proportion of Georgetown College students who say they get enough sleep at night is somewhere between 26% and 44.5%. Let's do a hypothesis test. But before we do the hypothesis test, let's remind ourselves about computing margin of error. Margin of error, again, is going to be the difference between one of our endpoints and our sample proportion, and that turns out to be about 9.4%. So that's a pretty big margin of error. And we're going to see again very shortly that there's a tie-in between margin of error and sample size. So hang on and we'll do that. Now for the hypothesis test. Our null hypothesis is that half students do get enough sleep. Our two-sided alternative then is going to be that that's not the right number, that some number other than 1/2 get enough sleep at night. So to use P norm GC, remember, we need to find how far apart the null value is from our sample proportion. And it turns out it's 0.1479, about 14.8 percentage points below the null value. So we need to go 0.1479 above. So we're going to add that to our null value, and we get 0.6479. We compute the standard error. 0.5 times 0.5 divided by 71, take the square root of that, we get about 0.06. And so using P norm GC, we're going to input our interval here. Region is outside. Here's our purported mean, our purported standard error. And we see we get a very small p-value, about 0.0122. So a little over 1% probability according to the p-value. So written as in the form of a sentence, if the null hypothesis is true, that is, if half of Georgetown College students say they're getting enough sleep on average, then we have just obtained a statistic from our sample such that it, or one farther away from 1/2, would occur a little bit more than 1% of the time, about 1.2% of the time. 1.2% is less than 5%, so this is a situation where we're going to reject the null hypothesis. And we say that we have strong evidence that half of Georgetown College students do not. The number is some other number. The proportion of students who say they get enough sleep is some number other than 1/2, and it seemed to be likely to be less than 1/2. Let's see how we do binomial test GC in this case. So it's going to look kind of familiar. We have to do a few different things here. We give it the variable name. So we're going to give tilde enough underscore sleep. We tell what data set it comes from. So we give the variable, the data set. We have to give the null value again. And in this case, because all our data lives in a single column, we have to tell what constitutes a success. So let's go over here to MAT111 survey and notice that the responses in enough underscore sleep are no's and yeses. So we need to tell our studio what constitutes a success. And so we have to give it a value that's actually in that data column. So we had to either put no or yes, since we were checking to see if enough sleep means that the answer would be yes. Do you get enough sleep? The answer would be yes. We're going to put yes as our success. So that's an important part here. When we're giving it access to data that's already loaded into our studio, we have to tell it what constitutes a success, and we have to get this text exactly right or it's not going to work. Because I was using a 90% confidence interval earlier, let's use a confidence level of 0.9. Our alternative is 2 dot-sided, and some of our output is here. Here's p hat. Here's our standard error. The confidence interval, very close to what we had before. Our p-value, again, is a little bit different. It's 1.7% rather than 1.2%, but we're still getting the same. It's close to what we had before, and we're drawing the same conclusion that we did prior. So as promised, let's talk about sample size and margin of error. So if we're dealing with a 95% confidence interval, then the expression for margin of error is the multiplier, 1.96, times the standard error, p hat times 1 minus p hat over n, square root of all that. It's an algebra fact. It's a mathematical fact. If you want to say, we could use calculus to show this, but we could show definitely that the margin of error is as big as it possibly can be when p hat is equal to 1/2. I'm not going to try to demonstrate that algebraically right now, but we could draw a graph and see that basically it's a parabola. The graph of the parabola has a peak when p hat is equal to 0.5. So if I put 1/2 into this formula, 1/2 times 1/2 is 1/4, and the square root of 1/4 is 1/2. And so if I pull the 1/4 out from underneath the radical, I can reduce this expression to 1.96 over 2 times the square root of n. If you want to ask about this in class, I'll be happy to do a little bit of derivation on this. So this is the expression for margin of error when p hat is equal to 1/2. So if I want to specify a particular desired margin of error, I can set this equal to that desired margin of error and solve algebraically for the sample size. And so if I specify m in advance, I can set 1.96 over 2 times the square root of n equal to m, solve that algebraically for n. Again, I can show this in class if you like. N then turns out to be 1.96 over 2m quantity squared. So if I wanted a 3%, 3 points of margin of error, 0.03 margin of error, I would double 0.03, that would give me 0.06. I would compute 1.96 divided by 0.06 and square that, and that would give me 1,067 plus. So if I sampled 1,068 individuals, then a 95% confidence interval would be guaranteed to have a margin of error of 3 percentage points. And so what that means is that when I ask a survey of size 1,068, then 95% of the time, my sample proportion will be within 3 percentage points of the actual true proportion. That's a pretty powerful statement. Just even if I have a population of millions, if I choose slightly over 1,000 well-selected, randomly chosen people, 95% of the time, the sample proportion I get from those 1,000 plus people will be within 3 percentage points of the population-wide proportion. 95% of the time, I'll be within 3 percentage points. So that's one reason why opinion polling, when it's done well, gives us reasonably powerful results. We don't have to ask that many people to get pretty close to the true value. And so you may pay attention to surveys that you see reported to you in the news. You'll notice oftentimes that the sample size is right around 1,000, and that's because they're trying to get to a 3% margin of error. So I'm going to end this with a couple of problems for you to try. We can talk about these in class. What sample size would we need to have if I wanted to have a 2.5% margin of error? So I'm going to let you try that problem. And then here's another problem for you to try using your by hand, to find a by hand confidence interval. Use pnorm GC to run a by hand hypothesis test, and then use our one-stop shopping command, binom test GC, as well, to answer this question. Do 60% of students at UC Davis prefer to sit in the middle of the classroom? So I'll let you work on this. We can go through this in class when we get together, talk about it, but I just want to give you a chance to work on this yourself. I've got some answers here for binom test GC. Your by hand calculations will be a little bit different from that, but this will give you a target of what to go for. So work on these, and we will talk about them when we get together.